All right. All right, so this is where we finished. So we were talking about variable types and scales. So what are the types of variables that we have? Generic types. Qualitative and quantitative, right? Of the quantitative variables, what could they be?
Numerical.
There, yeah, continuous or discrete. Continuous or discrete, right? All right, the scale then could be two different types based on each. So for the qualitative variable, what types of scale do we have available? Nominal and ordinal. What's the difference between those?
Ordering.
Yeah, ordinal has an implied or a natural order. Right, so magnitude increase. There's no, set scale. So going from a 2 to a 4 might not be the same as going from a 4 to a 6, but there's a clear order. All right, and then our scale for our quantitative variables are what? Ratio and interval. What's the difference between those? A meaningful 0 point. So if we have a meaningful 0, then ratios apply throughout the entire scale. If we don't have a meaningful 0, then ratios aren't going to apply across the entire scale. And the example is like degrees Fahrenheit, degrees Celsius, where that 0, that once you go into the negative, you start throwing off some of the ratios. All right? So up to this point then, with our definitions through the variable scales and types, I have a quiz that went live just now. All right? So the quiz, I did have it due date for the end of Thursday. I just changed it to the end of Friday. Just know that we might have another quiz that goes live on Friday that you'll have end of the day on Monday. All right? But it's about 10 minutes long, short quiz. I thought I was going to do this in class, but I thought if anyone ends up needing to be out for any reason, you have the opportunity to take it online. All right. Any questions on this? So here's a summary. Again, if we have count data, we can make those counts on nominal data. We can do it on ordinal, interval, or ratio. So like we can ask how many brown-haired individuals are there. So brown-haired is the nominal variable. We can make a count on it. And then we could do a frequency distribution of those counts. Same thing with ordinal. With interval and ratio, it's a little bit harder, especially if they're continuous. We probably have to round or do something called binning in order to get those frequency distributions. All right, calculating means or median and modes apply to ordinal interval. Order values doesn't apply to nominal. Quantifying the differences between each value applies. So this table just kind of gives you a summary. I can't even remember where I pulled it. It may be from the open textbook, just to kind of show you some of the relationships. No, I'm not going to ask you, to repeat this table or to replicate this table in any way. It's just to give you a summary. But do know that nominal or ordinal are qualitative variables. All right? If we have a qualitative variable, they'll be either nominal or ordinal. If we have quantitative variable, be it continuous or discrete, then it's going to be interval or ratio. But just because we have numeric data doesn't necessarily mean just because we have numeric data doesn't necessarily mean that we're quantitative. The Likert scale, that's numbers, that's actually ordinal. All right, and then we can always classify certain traits, characteristics based on their numbers as well. So we really have to think about what's the trait, what's the attribute being compared. All right, so again, why worry about the variables? Our statistical tests mostly depend on the type and the number of variables that we're working on. All right, so if we have qualitative variables, we're comparing frequencies. That's what we compare. Those are the types of tests that we use to analyze the data. If we have quantitative data, then we're typically comparing central tendency or dispersion. So we're comparing maybe means, averages, or we're comparing variances, and we're doing tests that allow us to do that sort of stuff. Right? The scale of the measure, however, has very limited influence on the test itself. All right, so whether it's ratio or interval, we don't really care. Most of our tests, if they work with interval, they'll work with ratio and vice versa. Same thing with categorical versus ordinal. There's tests that can be used both ways, or that can be used for both, so it doesn't really matter. Like a chi-square test, that could be used with either of these variable types. But we do have some specialty tests that take into account the ordering, that natural ordering of ordinal data, so that we can make conclusions about increases. You know, did something cause an increase in that scale, or that satisfaction scale, and so forth. All right. For the continuous and discrete, the biggest difference between these two would be in the display of the data. All right, so we don't really like to use a data type where our best fit lines are continuous when we have discrete data. Yeah, we can kind of violate that assumption, but oftentimes our figures want to exemplify the fact that we are working with discrete data, that it is whole numbers. Are we going to worry about that too much for this class? No, not really. I'll show you how to make figures, regardless of continuous versus discrete nature, and we can use those figures throughout the course. All right, more definitions. Our data interpretation really comes down to how well we collect our data. And one of the things that we always focus on is collecting a random data set. Having a representative sample, a random sample. Now, as we collect the data, there will be errors associated with it. All right? Our goal is to keep the sampling error the same for all of our analysis. All right, so what's our sampling error? That's a chance difference between our estimate and our population parameter. So what we can do, if we truly have a representative sample, a random sample, then we're minimizing our sampling error. If we truly have a random sample. Now, with our analyses and with our measurements, we always strive to eliminate bias, but we recognize that sometimes this just isn't possible. So what's bias? Bias is a systematic discrepancy between estimates and a true parameter. An example of this is if we were measuring heights, all right? And we're using a tape measure, but let's say the tape measure is off by 1 inch. All right? Maybe it was a misprint. All right, when we measure, everyone, we're going to bias our estimate because of the bias in that measure. All right, same thing with scales and weights. There's always some sort of error associated with it. Hopefully, the error is the same every time we measure, but if we know there's bias, we can correct for it. So these two terms, sampling error and bias, have an effect on the accuracy and the precision of our estimates. All right, so the accuracy of our estimates is affected by bias. That's our measurement. We're missing an inch off of it. Our estimate is going to be off, or is going to deviate from our true value. So what is accuracy? Accuracy is the closeness of our measure or computed value to the actual true value. It's how close we are. All right. Non-random sampling and instrument error could introduce bias. We talked about instrument error. We didn't talk about non-random sampling. How does that introduce bias? Well, let's say if we asked students on campus for their favorite class? Or let's say, what is their major? All right. We should get a random sample. So whatever our random sample is, we have the same frequency in our sample as across the campus. Now, if we collected and did our survey right on the steps of Cadmus, do you think we have bias in our sample? Yeah, we're getting a lot of science majors. We're going to see a lot of science majors in that sample. If we go out to MCS, right, do you think we're going to have bias there? Yeah. All right, so that's how non-random sampling can introduce bias. Sampling error affects our precision. So our precision is the closeness of repeated measures to, it's a closeness of repeated measures. So it's how well, when we make our estimate, do we get the same estimate over and over and over again. All right. Measurement error and sample size could affect our precision. All right, and these two things are kind of linked. Because if we have a sample size, a small sample size, and we have a lot of measurement error, our precision is going to be fairly. We're not going to have a whole lot of precision. But if we have measurement error and a large sample size, then usually that large sample size is enough to shrink the amount of measurement error that we see. Not always, but it's possible. All right. Of all of our variables, continuous variables are the most difficult to be precise, and it's because of rounding. Because we round our numbers, and we'll get to those. So here's a graphical representation of accuracy and precision. I know some of you that have had ecology have seen this. Some of you in ecology will see this. So these are bullseyes because that's a great way to show accuracy and precision. If we're accurate and precise, we hit our bullseye, we hit our target. All right. And because we're precise, our grouping is very, very close together. All right. If we're accurate but not precise, you can see how wide our shots are on this target. But if we take all four and take an average, our average is going to be right on target, right on the bullseye. All right. So we're accurate but not precise. If we're not accurate but precise, we're off our target. But because we're precise, our groups are real narrow. All right. And then if we're not accurate nor precise, we're off the target and we're spread out. All right. How does this affect means and variances? Well, if we put it in terms of our descriptive statistics, our mean is all about the accuracy. How close is our sample mean to a population? The closer we are, the more accurate we are in our estimates. Our dispersion, our measures of dispersion, so standard deviation, variances, confidence intervals, that is reflected in our precision. So the more precise we are, the less variance, the less standard deviation, the narrower our error bars are of our estimate. All right, any questions? Hopefully you've seen this before, at least someplace. All right, so we said continuous variables are the hardest ones to be precise, and it's because we round them. All right, so our heights with the tape measure. All right, we're eyeballing, figure out where our heights are, and we're going to have to round it at some point. Well, when we have a rounded number, that rounded number has an implied range. It's basically, here's our number, 60 inches. However we round it, that 60 inches could be within, let's say, 59.5 and 60.5 inches, if we round it to a whole inch. That is an implied range. So our implied range is the range of measurements where our true value lies. It's always going to go to one more digit than what was measured by the researcher. So this is what I mean by that. We measured something and it's 5.64. That's what my calipers said, 5.64. Well, there is an error rate associated with those calipers. So our actual value could be 5.64, but could also be as small as 5.635 and as large as 5.644. This here is our implied range. This is the number that we reported. This is our rounded number. All right, so when we say our implied range goes one more digit, we look at that last digit, that 4, and say, okay, well that could be either a 35, there's our one more digit, or a 44, there's our one more digit. Now, when we round, what are we aiming for in our data set? Well, we aim to have anywhere from 30 to 300 steps between our lowest value and our highest value. That's our target, all right? Does that mean we're actually going to get there? Probably not. Probably not. Sometimes you do, sometimes you don't. All right? But what we try to do is aim for enough precision to allow adequate variation for our statistical tests and our statistical methods. All right? So when we do this, let's think about the heights. If we measured heights in feet and we rounded everything to feet, we're going to have maybe 5 feet and 6 feet. That might be all that we have. Is that really enough to identify differences in height between, let's say, male versus females? Probably not, right? We're too broad of scale. We've rounded at too large a number, all right? So let's say then we remeasure, but now we're actually to the 1/1000th of an inch level. Do we really need to go that large, or that small, that fine? Probably not. I mean, at that point, we're going to get some instrument error associated with it. So how close are you at actually pushing it down, pushing the tape measure down on the floor? If you push too hard, you bend the tape measure, right, and affects your error. That would be our instrument error. So all I can really say with our rounding is that with practice, you tend to round at a spot that allows for sufficient variation to do our statistical test, yet minimizes the instrument error, whatever instrument that we're using at that time. All right. If you've had chemistry, you've probably learned some of this, right? Who's been in chemistry? All right. What does chemistry call it? Significant digits. What does that have? Where do you come up with significant digits? Yeah, based on what you use to measure. So what's our rule for those significant digits? Somebody's probably in that chemistry right now. What's that?
Isn't it 1 digit farther?
Digit.
One less.
Yeah.
1 less. Right?
Yeah, one less. So yeah, well, you have to look at the uncertainty. So I'll use the scale that I have upstairs. It goes to 1,000th. Now let's see here. I'll use my scale at home that measure in grams. It goes to the grams. All right, and it has like 5%. 5% error, I think is that scale. So, if I weigh out, 99 grams, that last digit is the one that can vary by as much as 5%. Right? We're going to be good at keeping to that, even according to our chemistry rules. But let's say we've got a large value. Chemistry might say, oh, we need to go up higher. Not us. We'll just keep with what we're using, with what's easy, because significant digits doesn't matter when it comes to stats. They will, though, when we talk about error, and you'll see why. So I wouldn't worry too much about this. But the implied numbers, the implied limits, does have an effect. So we measure, we calculate means, we calculate standard deviations. We don't ever report all of the decimal points. We actually have to round it. So how do we round? Well, the rounding rules that we're going to use are basically the same rounding rules that you've had all throughout grade school and all the way up today. So if our last digit, so whatever we're targeting, our rounded number, we go to that next digit and look at it. If that digit's less than 5, we leave our number, our target digit alone. If the last digit is greater than 5, we round our target digit up. The trick is, what happens if that digit is 5? If our last digit that we're looking at is equal to 5, what do we do? Well, then we have to go to one more digit. If it's 0, if it's a non-zero number, then we assume that this number, instead of being a 5, is slightly higher than 5, so we round up. If that number after the 5 is 0, or it's missing, meaning there's nothing else after it, then we just leave our digit alone. Now, this is what R does, and this is how we're gonna work with it. Some of you though may be thinking, okay, hold on, we're gonna bias our rounded numbers a little bit. And you're right, we are. So the textbooks actually have a slightly different rules that balances the how many times you round up versus how many times you leave that number alone. And they base that on our target digit. So if our target digit is odd, we round up. If the target digit's even, we leave it alone. Or you can reverse it. If it's odd, you leave it alone. If it's even, you round up. In that way, you're hoping to balance the number of times that you round up with the number of times that you round down if you have this situation where you have a 5 after it. All right, a 5 with nothing or it's missing. No more numbers after that 5. Are we going to do that? No. That's why I put it in a no. All right, we're going to do what R does. So if we round things by hand, you can use R to check your work, and hopefully we get the same answers. All right. So here's our practice. Got these numbers. All right. What I'm going to ask you to do is to round them to the appropriate number of digits. And this isn't significant digits. All right, so with our digits, we're rounding basically to the whole number. That's probably better. Round to the whole number. This, we're going to go to the hundredths place. Here, we're going to the thousandths place. Here, we're going to thousand, and then here, we're going to the tens place. So go ahead and do your rounded number, and then also, based on that rounded number, go ahead and calculate the implied range. I do have a column here for a rule. Basically, what rule did you use to round? To round or to not round? You can fill that out if you want, or you can just go ahead and leave that blank. The implied range is the implied range of our rounded number. You get it? I'm gonna have the implied ranges up here too. We'll talk through them. All right, so rounded numbers. Here's our target digit. And this is our target digit right here. All right, that's our 2 digits. That's where we're targeting. So we go to the next one. Is it less than 5 or greater than 5? Less than 5, right? We leave our number alone. So our rounded number is 13. All right, 2 digits. This is our target digit. We go to the next one, which is a 5. Is it greater than 5? Yep. Well, it's 5. So we go to the next number. Is this 0 or nothing? No, it's a 1, which means that this 5 is actually slightly larger than 5. So if this is slightly larger than 5, then we round up and we get 0.96. All right? 2 digits. We're going to here. There's our target. We look at the next number, less than 5. We leave it alone. We round to 0.011. 4 digits. Same thing. 3. We go to our next digit, less than 5. We leave that 3 alone. That's our rounded number. 4 digits here. We're 9. All right? So with that 9, we look to the next number. It's a 5. There's nothing after it. There's nothing to suggest that this is a little bit larger than 5. So because of that, we leave the 9 alone. So we keep it at 0.2789. Same thing here. We're rounding to that number. We go to the digit over, which is a 5. Nothing after that, so we leave the 8 alone. It's these 2 numbers here where we have that rule from the textbooks, where it would have said, some textbooks would say, well, if this is odd, let's round up. If this is even, we leave it alone. And that way, we kind of balance out the rounding up and rounding down, because if we have a bunch of these 5s with nothing after it, we're just leaving them all alone. We're going to bias our estimate down a little bit. Questions on the rounding part? Now, the implied range, I'm going to tell you, we will take the easy route. So I'm not going to worry about you adding a 1 after this 5 here. All right, we're just going to say our implied range for 13 means that our number could have been as small as 12.5 and as high as 13.4. All right. Now, according to our rounding rules, there's nothing after the 5, so we should have left this alone. We're going to make it easy and just say when we work with an implied range, 12.5 to 13.4 will suffice as an answer. If you did 12.51 up to 13.4, that could work. I'm not going to take off for it. All right. 0.96, our implied range, 0.955 up to 0.964. Again, we have 0.96. It could be any of these values in between here. 0.11, 0.0105 up to 0.0114. That's our implied range for this one. 3, 0.1953, 0.19525 up to 0.19534. 0.2789 is 0.27885 up to 0.27894. And then our last one, 8, again, goes 1259.75 up to 1259.84. Things to note. Notice, our rounded value, the implied range of that rounded value does not capture that. All right? That's because of some of our rounding, especially when you have nothing after that 5. All right? We're going to see it. We see it in both cases here, where our implied range did not capture the actual value. But for the most part, I think we captured our value for all of the rest. All right. Questions? You might be wondering, why worried about implied ranges? When we utilize measures in equations, so if we utilize a mean, Well, the mean has its own implied range, or has its own implied variance. We have to account for that if we take averages, if we take, let's say, two measurements to do, let's say, surface area to volume ratio. Each of our measures, surface area and the volume, has an implied range tied to it. That is going to magnify in our error of that ratio itself. And we'll show you how that works. But first, let's go over rounding in R. Rounding in R is actually really easy. The function is round. Round, you specify the number that you want to round, and then digits is how many places you want to round. Now, the digits actually refers to decimal places. All right? Actually refers to decimal places. So digits equal 0 is our ones place. Digits equal 1 is our tenths place. We want one decimal. All right? So here's an example. Round the number x to, or round 2.567 to 2 decimal places. How do we do it in R? We type in round, parentheses, 2.567, comma 2, digits equal 2. Let's go ahead and do that. Just make sure you get it. And this should reflect exactly what you would have rounded if you did this by hand. Should have worked, right? What if we wanted to round instead of decimal places to like the tens place or the hundreds place because we're working with a big number? Well, then for our digits, we're going to have to use a negative. All right, so as I said, a 0 represents the ones place. If we wanted to round to the tens place, we use a -1. All right, so if we're at a 0 there, so digits equal 0 rounds to the ones place. Digits equals -1 rounds to the tens place. -2 rounds to the hundreds place. So go ahead and do that example. Just make sure we get the same answers. Get it? Good work. Okay, mine's got -2.
After 3, I'm not saying that.
Yeah, no, you're not crazy.
Cool, thank you.
Maybe the
You were
PDF
there
though?
for a moment.
PDF, what's that? Yeah, because you use -3. Is yours up here to -2? Yeah. Yeah, that's it must be an issue on that PDF. So up here on the board I've got this, but you can easily mess around with it just to see how it changes. Let me open up my order. Take this out. So round x digits. Okay, first, x digits. Round x to digits, decimal places. Negative digits, round to the left of the 1. There we go. All right, so yeah, round, just make up a number. Rather large number, just to kind of demonstrate it. If I do digits equal 0, or just 0, right, and run it, it rounds to the whole number. If I start going -1, it's going to go to the tens place, -2, goes to hundredths, -3, goes to thousands, -4, goes to 10,000, and so forth. All right, so pretty easy. And R is going to use the same rounding rules as us. And we're doing that for a reason, so that way if you round, you can use R to check your numbers. There are two other things that R can do, and that's ceiling and floor. Ceiling is when you round a number up to the highest whole integer, or the next highest integer. Floor is when we round down to the lowest integer. Do we ever do this? Usually not. Usually not. Time you would is if you are binning. So binning is taking numbers and adding them to groups, especially if you have continuous numbers. Maybe you're grouping them into integers by integers. So like here's all the values from 1 to 2, and then 2 to 3. Maybe you use floor in that case, or you can round up, say all the numbers up to 1, and then up to 2, and so forth. We typically don't do it by hand because usually we're making histograms, and we let R make the histogram for us. Do all of that behind the scene. All right, so here's an example for R. All right, so here's our examples. Here's our numbers. This is probably how you would see it on any quiz or exam, where I give you the number and then I'll tell you what digits. Hundredths place, tens place, lowest integer, highest integer. Just go ahead and get these numbers. I have code, right? If you do it in your R, have a markdown document or whatever, then you'll always have the code, and we'll double check these numbers, but also come up with the implied range, just as practice. Give you a few minutes for that. Yep. The negatives just moving to the left of the ones digit. If you remember, digits equal 0 gets to the 1. And if we go positive, we're going into the decimal regions. If we go negative, we're going to the left of that. And again, I think everyone knows how to round. You can always check your answers. So if you type some code and you're like, yeah, that doesn't look right, maybe your code's wrong. Yep.
Is there a way that you'd be able to insert that without having to go back to a tasks like
Yeah. Did you open it? Did you open one? Did you save it? Yeah, go. Assignment, are you opening up? Okay, so do you want to make it markdown? And we always just go one more digit. We don't worry about anything after that. How are we doing? Good? Yep, all right, here's my R. Okay, practice 15.679. 2, you're going to the hundredths place. So 15.68. Our implied range, again, it's basically the lowest number that would round up, the highest number that would round down, but we're going shortcuts. So this is 15.68, so 15.675 up to 8.4. There's our implied range. Round to the tens place, so using -1, because we're going to go 1 to the left of the ones place, we get 180, so our implied range is 175 to 184. Again, 175 should round to 180, 184 rounds to 180. Here's floor. So if we were just rounding to the integer, this should have rounded up, but floor takes us down, takes us to the lowest integer. So you can see then the implied range, if we follow the same rules for the implied range, all right, it would be from here to here, but again, we use floor, so if we were always using floor, technically that wouldn't be our implied range at that point. This is more. I don't think I've ever asked for an implied range anytime you've used floor or ceiling. Just to avoid confusion. Just to avoid confusion. So here's ceiling. Again, rounds it up to 4. If we were doing an implied range of 4 and that was rounded, it'd be 3.5 up to 4.4. This one. We're going to the 4 digits. So we're rounding to that point. Here's our rounded number. Our implied range is 1.79675 up to 1.79684. Tricky one is this last one. All right, we're rounding here to the hundredths place. We're rounding at that 9. If we look at that next integer, it's greater than 5, so this number is going to get rounded up. That goes to 0, that bumps this up to 9. So now we end up with 39,000. This is where your significant digits, where you might have to mark it on your answer sheet, in chemistry, where you'd say, okay, that's our significant digit. So then our implied range refers to that 0, not to the 9, because that's not where we rounded. We rounded at this point, the hundredths place. So our implied range would be the 38950 up to 39040. Our implied range should capture the actual value that we rounded. The exception though comes when we have 5. When that next digit is a 5 and we don't do anything. All right. Let's call it here, because next up is derived variables. We'll pick these up on Friday. I'll leave this up right here. And I do think I've got some practice. I have to look at the homework. Yeah, don't forget the quiz. Review definitions, review variable type scale. That's going to be important. You'll see it again on the exam. You'll see it not only on exam 1, you'll see it on the final exam, and those of you going to grad school will also see it in grad school too. It's important to know those.